Okay, can you make sure you please have some paper ready and a pen to take notes? Remember, because it's a video, you've got the luxury of being able to listen to parts again if you need to. So take the advantage and rewind to think and repeat bits if you need to. There will be places you're asked to pause the video and complete an activity. Make sure you take a picture of your work and email it to your teacher after the end of the lesson, please. Here's your starter questions. If you can pause the video here, please have a go at the starter questions and then press play when you're ready to check your answers. Let's have a look at those answers then, see if they're right. Okay, first of all, the probability of getting a 3. There's 1 3 out of 5 sections, so the probability is 1/5. We've got a two-way table here, and we have to put all of the correct information in. So we've got 62 of the students were male, so the total needs to be 62. Out of the 43 students who pick chips, so chips was a total 43, 19 of them were female, which means you can then do 43, take away 19 to get the 24. All of the 29 students who pick burgers are male. So the burger one, all 29 there, and they're all male, which means there's a 0 in the burger at the top. So you've got all of the burger one filled in. If you know the 24 and the 29 add something equals 62, take 24 and 29 away from 62 and you're left with 9. Okay, and if you've got 62 in the total and we know there was 100, you can get the 38. We've got the 0 here as well. So we've got 100 here. We know the 29, we know the 43, so we can get the 28 here, which means we can work out the 19. And 0 and 19 add something here was 38, so we can add another 19. Down here, remember probabilities all have to add up to 1.00 or a whole one. So calculate the probability of picking a pink. If you add 0.14, 0.62 and 0.2 together, take them away from 1, you're left with 0.04. Calculate the probability of picking a blue or a grey counter. We need to add 0.62 and 0.2 together to get 0.82. Okay, in a box there are 3 yellow balls and 6 red balls, which means there are 9 balls altogether. Okay, the ball is picked at random, the colour is noted and then put back. The second ball is then picked at random. Draw a probability tree to show the outcomes and use this to calculate the probability of picking 2 balls the same colour. So you could either have yellow, yellow, or red, red, and you need to then add those branches together. Okay, so for the yellow, yellow, you should have done 3 out of 9 times 3 out of 9. And for the red, red, you should have done 6 out of 9, add 6 times by 6 out of 9. And then added your 2 probabilities together and it simplifies down to 5/9. Right, today's lesson is on experimental probability. If you can write the title, please. So here we have Dave, and Dave has done a little mini experiment using this spinner. So it's a spinner and it's got 4 sides, it's labelled 1, 2, 3, 4, and he spins the spinner and he's recorded his results, and after 5 spins he's got the results: a 2, a 2, a 3, a 2 and a 2. And Dave thinks that it's not fair because it's landed on 2 much more than he would expect. So if it's a fair spinner, you would expect it to land on all of them around once, okay? But what conclusions could we make from the data and how could we improve that? So is it fair to say, after spinning it 5 times, that it's a biased spinner? Or could it be that he's just unlucky and it's landed on the 2s more than it should? Okay, what we could do is we could do slightly more spins. So this one then, we've got data now. So Dave spins a spinner 20 times and makes a bar chart of his results. It now looks like it actually lands on 3. So that goes against his previous assumption. 2's still up there, but 4's creeping up as well. Okay, so what we could do is we could do more spins. And now we've got 200 spins and he's made a bar chart, and as you can see, this is much more what you would expect from a fair spinner. It's landing roughly on the same amount of times. The bar's about the same height. So if we're spinning a spinner 200 times and it was perfectly fair and it has 4 sections, we would expect it to land on 50 each time. And you can see from these bars that they are around the 50 mark. Okay, what we can conclude then, if we carry this on, so he did 5 spins, 20 spins, okay, and then you can increase it all the way up to, if he did it 1,000 spins and it recorded just the number of 4s, okay, it would land on a 4 252 times, okay? So that's almost a quarter of the times, which is exactly what we expect, okay? So we can work out the experimental probability. That's the probability recorded after you've done an experiment by doing the number of 4s it occurs over the total amount of spins. So 0 divided by 5, 3 divided by 20, 17 divided by 80, 23 divided by 100, and 252 divided by 1,000. Okay? Theoretical probability is the probability that we expect. So if we've got a fair dice with 4 sections, we would expect the probability of it landing on a 4 to be 1 out of 4, or as a decimal, 0.25. And as you see, as you increase the amount of spins and the amount of experiments, this probability, the experimental probability, is getting closer and closer to that 0.25. Okay, in general, the more experiments we do, the closer our experimental probability will become to theoretical probability. Okay? In a test, if you're ever asked which is more reliable, it's always the one with the more experiments, okay? The more number of trials, okay? It will become closer and closer to theoretical probability, okay? Key point then, can you write down that more trials equals closer to theoretical probability? You also might want to write down that theoretical probability is the probability that we expect to happen, okay? So, for example, that we expect the probability of a fair dice and it to roll in that and it landing on a 6 to be 1 out of 6. That's the theoretical probability. Although if we was to roll a dice 6 times, it might not land on all of the numbers once out of the 6 rolls. Okay, so just to reiterate the fact about more experiments, we've got Dave and Mary. They're doing separate experiments and they're checking if this spinner with 5 sides is fair. So they're going to look for the number of 5s it counts on. So Dave has done 50 spins and Mary has done 100 spins. Dave's got 8 5s and Mary's got 22 5s. So their experimental probability will be the number of 5s over the number of spins. Okay, so 8 divided by 50 to get 0.16, and Mary's would be 22 divided by 100 to get 0.22. Okay. The theoretical probability of it landing on a 5 in this case, okay, I mean, there's 5 sections and one of them is a 5. So the theory would be that it would be 1 out of 5, or as a decimal, that's 0.2. So you can see that the most accurate estimate would be Mary's, and that's because she did more trials. Okay, so how are we going to use this then? Okay, so Ash flips a coin 100 times to test the probability of the coin landing on tails. So she's done 100 flips and it landed on tails 45 times. The theoretical probability of a coin landing on tails is 1 out of 2, or half, or 50%, because there are heads or tails and only one of them should be tails. Okay, the estimate then of the experimental probability is actually the number of times it occurred in the experiment over the total amount of trials. In this case, 45 out of 100. So we'd actually use the experimental probability of 0.45. Experimental probability is also known as relative frequency. You will probably be asked to calculate the relative frequency more often than the experimental probability. They mean exactly the same. It's just usually called experimental probability because it's a probability that comes from doing an experiment. Okay? You do it exactly the same way. You do the number of times the outcome occurs over the number of trials. So the answer is still the same. It's just a different name. Right, let's have a look at this one. This one then is the example I would like you to copy down. So can you make sure you've got this copied down, please? You may need to pause it to catch up and copy it down. So Mo wants to find out the probability of seeing a blue car on his road. To find the probability, he conducts a survey and records the data. So he notices that there are 10 blue cars that go past and 40 not blue cars that's on his road. Okay, he wants the relative frequency of a car being blue. So first of all, how many times was the car blue? It was 10. And how many times cars were there altogether? There was 50. So relative frequency is the number of outcomes occurred, which is 10, over the number of trials. There was 50 cars altogether. So that's 1/5 or 0.2. Can you make sure you've got that down, please? Okay, another one then. So same process. We've now got Terry wants to find out the probability of seeing a red, green or black car on his road. So he's recorded the colour out of 200 cars as it passes by. So 200 cars, if you weren't sure about that, you could always add up the number of cars separately. So the relative frequency for a red car would be the number of red cars out of how many there is altogether, which is 200. So we're going to do 26 out of 200, which would be 0.13. Green is 19 out of 200, 0.095. And black is 80 out of 200, which is 0.4. Okay. Right, a little bit further on then. So first we've got to find a relative frequency of scoring a 6, and then we're going to use how many times the spinner was spun altogether. Okay, so first of all of the probabilities of a relative frequency, or because it's an experiment, should add up to a whole one. So if you add all of the relative frequency together, they have to total one whole one. So if we add up what we've got, 0.1, add 0.1, add 0.3, add 0.25, add 0.05 equals 0.8. The relative frequency that goes in the 6 is whatever we're going to add to 0.8 to make up to a whole one. So if you do 1 take away 0.8, you get 0.2 as the relative frequency. So we're working it backwards now to work out that frequency. We're trying to use this formula that we've already got here. We know the relative frequency. We don't know the event frequency or the total frequency, okay? So we've got to look at the relationship between them, okay? So when we've got a frequency of 0.1, a relative frequency, of 0.1, the frequency is 40. So if we've doubled the relative frequency from 0.1 to 0.2, okay, then we can rearrange that one. We could have worked it out a different way. I would have times that by 2 to make this one 80 and added those up. However, you can't rearrange it. So we know, using the formula up here, the relative frequency would be 0.1. The frequency is 40, put it in the right place. And we don't know the total frequency. We've got to shuffle that around. So you times by the total frequency, divide by 0.1, you get 0.4. The other way is to go, if that's 0.1 to 0.2, this number here would have to be times by 2 and be 80 as well, and you could add all of those together. Here are some questions I'd like you to do, please. If you could pause the video, have a go at working them out, and press play when you're ready to check your answers. Okay, let's have a look how you got on with those. So the answers for the first one. So experimental probability of choosing a sandwich, we've got 45 over 100, which goes to 0.45. Next one, relative frequency the bus is late is 23 over 50, which is 0.46, and the on time is 27 over 50, which is 0.54. Okay, so relative frequency for each one. We need to add up the number of trials to work out how many trials there were altogether. And then you're doing 32 divided by 200, which can simplify down, okay, to 0.16, 64 out of 200 to make 0.32, 18 out of 200, 0.09. You could write it as a fraction in its simplest form. That's what these are. 56 over 200 to make 0.28. 30 over 200 to make 0.15. Do we think it's fair? Probably not. Okay, these are all very uneven. You would expect them for a probability that there's an experiment that's happened 200 times to be starting to even out. These are all very different. 2 is really, really quite small. 3 is really, really quite small, and 2 is much bigger. Okay, last one. A bag contains 400 cubes, red and green. Fred experiments by picking a cube at random and then replacing it. So he's done an increasing amount of number of trials, 10, 50 and then 200. And the amount of red cubes was 4, 14 and 62. So the experimental probability is going to be the red cubes over the number of trials. So 4 divided by 10 to get 0.4, 14 divided by 50 to get 0.28, 62 divided by 200 to get 0.31. How many red cubes do you think they're in the bag? Well, the most reliable one we could use, okay? Oh, sorry, if you picked 150 times. So we're going to do... Oh, that's the second question. I think they're in the bag. So we've got 0.3 times by 400. Okay, so there's 400 here. So we're estimating, so there's around 120. Okay, and if you pick 150 times, how many might be red? So you're doing your 150 times by your previous 0.31 to get your probability of 0.45. Okay, moving on. So here are some more exam questions for you to do. If you can pause the video and press play when you're ready to check the answers. Answers are here. Can you make sure they're marked, please? Right, there's one more activity for you to do. You will need a coin for it. Can you conduct a probability? You need to do 50 trials. You need to do a tally chart, and you're recording how many times you're going to score tails. I'd like you to do your experimental probability, plot it on the graph, and answer the questions, please. Everybody's for this will be slightly different. Okay, make sure you send a picture of your work to your teacher, highlight red, amber, green, purple, and how you feel like you've done.